Hello again. We are talking about applications of cross product of two vectors in three dimensions. So one application is uh, to find the area of a parallelogram. We can use cross product, believe it or not. You know from elementary school that the area of a parallelogram is base times height, very simple. So we have two vectors here, the two adjacent sides of a parallelogram, vector u, vector v, they're making an angle of theta, and of course the distance between the two parallel sides of the parallelogram is the height of the parallelogram, and base times height is the area of the parallelogram. Now that height is nothing but hypotenuse u times sine of theta, because you know that sine of theta is nothing but opposite over hypotenuse using basic trigonometry. So if you want to find the opposite side, you just multiply the length of the hypotenuse by the sine of the angle theta. Magnitude of vector u times sine theta is the height of the parallelogram. And we know that area is base times height. We know the height, but the base is actually the magnitude of vector v. So if you multiply magnitude of vector v by magnitude of vector u by sine theta, this is going to be actually the area of a parallelogram whose two adjacent sides are vectors u and v. Now, this comes from the definition of a cross product of two vectors. You know that magnitude of u times magnitude of v times sine theta is actually the magnitude of the cross product of the two vectors u and v. So all we need to do to find the area of the parallelogram, you find the cross product vector and you find its magnitude. Boom. That answer you get is going to be the area of the parallelogram. Now, you know that a parallelogram can be cut into two triangles by drawing the diagonal. So if I draw this diagonal here, we know that we are cutting the parallelogram into two triangles, and the area of each one of those triangles would be 1/2 of the area of the whole parallelogram. So this helps me to come up with a new formula for the area of a triangle. For the triangle, we always knew that base times height divided by 2 is the formula. But now we see that if you find 1/2 of the magnitude of the cross product of the two vectors, u and v, that are the two adjacent vectors in a triangle, then that formula will give you actually the area of that triangle, believe it or not. So right now I have 3 points in the space. One is here, one is here, one is here. So 3 points in the three-dimensional space, A, B, C. And this triangle, imaginary triangle up in the air, I want to find its area, believe it or not. So the first thing I'm going to do, I'm going to find the vectors. So I'm going to find vector AB. So it's going to be vector AB. And of course, it's x of b minus x of a, y of b minus y of a, and z of b minus z of a, right? So we go 3 minus minus 1, which is 4. Minus 1 minus 3 is negative 4. And 1 minus 4 is negative 3. So that's vector AB. Let's say this vector right there. And the other vector I'm going to find is going to be vector AC, because I want to have two adjacent sides of the triangle. I want to get two vectors that are playing the role of two adjacent sides of the triangle. So this is going to be AC. So again, x of c minus x of a, y of c minus y of a, and so on and so forth. So I'm going to go 5 minus minus 1 is 6. 1 minus 3 is negative 2. 1 minus 4 is negative 3. So I found the two vectors AB and AC. Now I'm supposed to find the cross product of these two vectors, right? So I'm going to do that here. I'm going to go 4, negative 4, negative 3, 4, negative 4, negative 3, and then 6, negative 2, negative 3, 6, negative 2, negative 3, right? I draw my box, and then I do the crisscrossings here. So I'm finding AB cross AC, the cross product of these two vectors, okay? So that's going to be 12, okay, minus 6, which is 6. This crisscrossing will be negative 18 plus 12. That's negative 6. And next one would be negative 8 plus 24. So that is 16. Okay. Now that I have the cross product, I have to find its magnitude and then times 1/2. Okay, so how do you find the magnitude of this vector? It would be 6 squared plus -6 squared plus 16 squared. Take the square root of that. That would be the magnitude of AB cross AC. Okay, whatever the number will be, maybe it will be 328. So 328 on the dividing cross sign. This is actually the area of the parallelogram in square units. But we're looking for the area of the triangle, okay? So 1/2 of that. So I'm going to say area of triangle equals 1/2 times square root of 328. We have to simplify the answer. So it's going to be square root of 82 because 328 can be simplified as 4 times 82, and square root of 4 is 2, so we end up with 2 root 82 times 1/2, which is square root of 82. Now I'm going to write down here square units. Okay, why square units? Because it is the area of the triangle end of the day that we are calculating. So you see how beautifully this idea of cross product is used to find the area of a triangle, believe it or not. So that was one application. Another application is when you have a solid called a parallelepiped. Parallelepiped is like a rectangular prism, which is like pushed to the right or pushed to one side, and it is like sort of slant kind of a rectangular prism. So you see that I've drawn this parallelepiped, which looks like a rectangular prism where all the angles are like sharp 90-degree angles, but right now it is not because it is like sort of slant. Okay, and we have the base, which is a parallelogram, like I talked about it before, and the two adjacent sides of this parallelogram are vectors u and v. And now to make it 3D, we have a third vector w here, and these three are three sides of this three-dimensional solid known as parallelepiped, and we want to find the volume of it. Okay, end of the day, it's a prism, and the volume of every prism is found by multiplying the area of the base by the height of it. Okay, area of the base is actually the area of the parallelogram. Okay, this area can be found using the cross product formula. Now all I need is actually the height, which is the perpendicular distance between the upper face and the lower face of the parallelepiped. And to find that, we know that this vector w is not completely vertical and straight. It is making an angle of alpha, let's say, with the vertical end of the day. Otherwise, it would be a rectangular prism, which is not. So if it's making an angle of alpha with the vertical, to find the height of this parallelepiped, I have to multiply the hypotenuse by the cosine of this angle alpha, because we know that hypotenuse times the cosine of the angle will be the adjacent side. Cosine is defined as adjacent over hypotenuse, obviously. So if you multiply the hypotenuse by the cosine of the angle, then it will give you the adjacent side length, which is height of this parallelepiped we're looking for. So H equals vector magnitude of vector W times cos alpha. So volume is area of the base, as I said, volume of the prism. So I put here prism volume. Prism doesn't have an E, so okay. Prism volume equals area times height. The area is U cross V, its magnitude, or actually not. Yeah, it is the magnitude. Yes, so it's magnitude of U cross V, and then we multiply this by the height, which is magnitude of W times cos alpha. So this is what we end up with so far. Okay. Now we have one vector times another vector, of course, magnitudes of those vectors, times cos alpha. This reminds me of the definition of dot product, if you recall. What was dot product of two vectors? Was magnitude of the first vector times magnitude of the second vector times cosine of the alpha in between those two. And we know that the direction of u cross v is exactly in the direction, vertical direction that is perpendicular to the parallelogram. So if this is the direction of u cross v, okay, and that is the direction of vector w, they are indeed making an angle of alpha with respect to one another. So this is perfectly matching with the definition of dot product. So basically all I have to do is to find the dot product of the two vectors. So vector w dot product of that with u cross v basically. Okay, so u cross v is a vector itself, and w is a vector, and I'm finding the dot product of two vectors, end of the day. But you see that here we have cross product and dot product both present in the same formula. This is known as triple scalar product. Okay, so triple scalar product is when you have three vectors and you're finding cross product of two of them, and then whatever the outcome was, you're doing dot product with the third vector. And such a thing is called triple scalar product. And here I have a numerical example. Well, we have vectors u, v, and vector w. And we can find the cross product of u and v, and then find the dot product with w. We will end up with a scalar as the answer, because it's a dot product at the end of the day. So triple scalar product has an outcome which is a scalar, which is a number, a real number. And that real number would represent the volume of this parallelepiped in cubic units. Okay, so we may do this calculation. I was thinking I wanted to do another question, but let's finish this up. Or actually, you can do it by yourselves. Find the cross product of u and v. Okay, it's not that hard. And then whatever the outcome was will be a vector end of the day. Because I don't think I have any solution here to save time. And then whatever the outcome was, you find the dot product of that vector with this. Okay. I don't think I have it here. And it is very challenging to do questions in like minimal time. It was some sort of experience end of the day. But anyway, so you can do this. It's not that difficult. Another thing I want to mention is that whenever you have a plane, okay, let's say you have a plane in the space, and there is a whole bunch of vectors there. Maybe this is vector u, this is vector v, and this is vector w. Okay, there's three vectors on it. We call these vectors coplanar. Coplanar vectors. What does that mean? It means three vectors that are lying on the same plane. Just like I have this piece of paper here, and I have one vector here, another vector there, okay, and maybe another vector like this. Okay, so these three vectors right now are coplanar because they lie on the same plane. So what we do to show that three given vectors are coplanar or not, this is what we do. We take two of them, okay, and we find the cross product of those two, okay? It will be a vector like this. And if this vector happened to be perpendicular to the third vector, okay, then in that case, it shows that the three vectors must have been on the same plane. Why is it like that? Because the cross product vector is perpendicular to the plane. And when it's perpendicular to the plane, it will be perpendicular to any vector in the plane, okay, including that third vector. And when you find the dot product of that cross product vector with the third vector, and that dot product happens to be 0, what does that tell you? It tells you that the two vectors are perpendicular, which means that this third vector must have been on the plane, otherwise the dot product would not be 0. The dot product of u cross v would not be 0 when you're doing the dot product of u cross v with vector w. So this is one way to show if three given vectors are coplanar or not. For example, we have 4, 3, 1. So 4, 3, 1 is one vector, and then the other one is 2, 5, 6. And we have another vector, 10, negative 3, 10, negative 3, negative 14. Okay, so we have three vectors. We just want to know if these three vectors in the three-dimensional space are coplanar or not. Is it possible to draw a plane or to pass a plane through all three of these vectors? Yes or no? That's the question. So what we do U cross V dot W. So we find U cross V, and U cross V is 13, negative 22, 14. So this is U cross V, and we're going to find the dot product of this with the third vector, which is 10, negative 3, negative 14, okay? And this dot product, you know how to find the dot product, is when you do the math, you get 13 times 10, which is 130, minus 22 times negative 3 is positive 66, and 14 times 14 is 196 negative. So when you add them up, surprisingly, you get 0. And if you get 0, it means that the three vectors must have been coplanar. If you didn't get 0, if you got some different answer, it means that the three vectors must not have been coplanar like this, okay? Must have been like that. Okay, you see, these vectors are not coplanar. But if all of them can lie on the same plane like this, then they are coplanar. This situation, coplanarity, happens when the triple scalar product is 0. And when it is not equal to 0, that is when the vectors are not lying on the same plane. They're not coplanar. Okay? All right. I think this wraps up this vector unit. You see, it's a beautiful world of mathematics there, but unfortunately, circumstances were in a way that we had to go through these very fast. And so it's all up to you to sit down and review and study and watch these lectures multiple times, stop them, hesitate about them, think about them, rewind, watch it again, write it down, take some notes, try the questions, redo them to see if you can get it. And this is taking obviously a lot of time, I understand that, but nothing is gained without great labor in life. Obviously, that's how it is. So, but I try to cover everything, I should say, everything. So hopefully you will find them useful. We will have one more unit on three-dimensional planes and equations and all of that, and then the course will be over. So good luck and stay safe, please.